So for 2-3, we are working with the derivative now as a function. In 2-2, we found the derivative at a specific point, but now we're going to think of it as its own function, so we can find the derivative at any point that we choose. So our objective here is, one, to find that derivative using our limit definition. And then the second one here is to look at a given function's graph and with that sketch the derivative. And then this bullet point here is just to interpret what that derivative graph is telling us with respect to the original function. So let's do a warm-up, and we'll come up with the theorem once we identify a couple of things. So here is this random graph. We are going to look at slopes as being positive, negative, or maybe zero at specific points. So, and remember, I'm looking at what that slope is, what that rate of change is at a specific point. So let's start with A. I think at A, we would see that this is a good sketch about what that slope would be, and that is a positive slope. With respect to this graph, let's call it f of x. We recognize that at A, my graph is increasing. It's got a positive slope, and then if I'm reading that graph of f of x, it's increasing. What's going on at B, folks? Looks like I have a negative slope, and if I'm looking at f of x, it's decreasing. C, same. I've got a negative slope. Looks like it's still on that decreasing end of f of x. And then if we continue, at D, looks like it's a positive slope and it's increasing at D. Negative, negative. What do you think? Negative, decreasing. G, looks like a positive slope and it's increasing. And then lastly, what is that trend? H has a negative slope. It is on the decreasing end of f of x. So graphically, this is what the derivative tells us with respect to our graph. If my derivative is greater than 0, if my derivative is positive, if the derivative is positive, my function is increasing. And if my derivative is negative over a specific interval, then I know that my function must be decreasing. So here we are. I'm going to take you back to 2-2, and this is when we talked about the derivative at a specific point A. Keep this in mind. We are going to come up with two different definitions, but I'm going to save that second one for later. But this is our limit definition of a derivative at a specific point. What makes this different? Well, in place of A, now I'm using x, which allows me to then find the derivative at any specific point. So in 2-3, we're going to be asked to find the derivative function of specific f of x's using the limit definition, whereas the one above it is at a specific point. So now we're going to translate this into a graphical question of how can I look at a graph and come up with what the derivative function may resemble. So let's do those next. So here are some guidelines that we are going to use when we are asked to sketch a derivative function. So keep in mind, when I'm sketching a derivative function, I am sketching slopes. I'm going to be sketching slopes. Oh my goodness. So what is step 1? We are going to find all of the points where my slope is 0. And then we're going to use those as a jumping off point. So easiest thing, we're going to locate where those zeros are for our slopes on our original function. And the next step is then to the left and right of those zeros, we're going to find whether or not our slopes are positive and increasing, maybe positive and decreasing, or negative. And we'll do several examples. And then we just connect the dots and smooth that graph out. This will seem very strange initially, but then you will get the hang of it. Let's do some problems. So here's our first example where we are sketching the derivative of this f of x graph. Let's be mindful of one thing. In this graph, the ordered pairs are x and their corresponding y values, whereas when we're sketching the derivative graph, we're going to be sketching the ordered pair x and its corresponding slope at that x value. So let's do step one. Step one is finding the x values where the slope is 0. Another way of saying, let's find the horizontal tangents. So if we look here, it looks like I only have that one horizontal tangent. So at x equals 0, I'm going to have a slope of 0. And remember, in this graph, I am sketching x and the corresponding slope. So let's continue. And maybe let's look to the right of that 0. And I'm going to clear this off. And what I mean by that is, if I'm looking at these slopes, what do you think? Are they positive or are they negative? And I'm hoping you're looking at that sketch and thinking, that's a positive slope because it's rising just a little bit. And then what happens as I keep going to the right? I think we see my slopes are positive and they're becoming more positive. So I might end up with slopes that look like this. Maybe at 1, for example, we would say, oh, at 1, that slope looks like it's a slope of 1. Whereas at 1.5, that slope is a little bit steeper. So maybe it's 1.3. And we see that trend. As my x's increase, I'm seeing that my slopes become steeper and steeper. So my slopes are increasing as well. Now let's look at the other side of that slope that we just had at 0. What are you noticing here? That is a pretty steep negative slope. So maybe at -2, that slope was, I don't know, like -3, right? So I'm going to put that ordered pair right there. But then what is the trend as I'm getting closer and closer to that slope of 0? And I'm hoping you're identifying my slopes are still negative, but what? Are they becoming more negative or less negative? They're becoming less negative. I've gone from a super steep negative slope to a gradual slope of 0. So I know that as I'm getting closer to my x equals 0, my slopes are becoming less negative. And so my derivative graph for 1 would look like this. So if we follow that same concept here, if I'm looking at this graph number 2, I would try to locate where that slope is 0. Except here, we do not have a slope where it looks like it's 0. So we're just looking now for a pattern. So as I'm getting closer and closer to 0 from the right, it looks like that slope is super steep and positive. Super steep and positive. So let's say slopes values are up here. Super steep and positive. But what happens as I'm getting closer and closer to 1 and then 2? Looks like my slopes are still positive, right? But here they're dramatically positive. And here they're positive, but they're becoming less positive. So it looks like as I'm getting closer and closer to 2 to 3 to 4, and then they look like they're starting to taper out a little bit and get closer to 0. So my derivative graph for number 2 might look like this. Now let's look at this one as another example, and then for the others I will just sketch what those derivatives look like. Again, the derivative is going to be the slope. So I see here it is slightly negative, but close to plateauing, close to 0. But as we get closer and closer to the 0 from the negative direction, our slopes are steep and negative, which means they are getting smaller in the negative direction. So, interestingly enough, the graph of that derivative for that first branch looks like itself. They are spitting images of each other. However, this second branch, what do you notice? Close to zero, those slopes are steep and negative, but becoming less negative as our x gets bigger and bigger. So it looks like this for the derivative for the second branch. So when we start to algebraically calculate these derivatives, here are some very useful derivative rules that we will apply. The first one is knowing and identifying that if we have a constant function, and remember these look like y equals -3, y equals 4, or in that notation f of x equals 6. But the rate of change, remember, which is the slope, this is a horizontal line, will always be 0. So I could say in this example that y prime, that's the slope, would equal 0. For all three of these, y prime, would equal 0. And here we would identify it as f prime of x would be 0. Now let's look at any linear function. We already know that that rate of change is constant because it's m. The rate of change will always be m for a linear function. Y equals 7x minus 8. My derivative, the rate at which that function changes, is always the slope. F of x equals 2/5 x minus 1. The slope, the rate of change, will always be 2/5 for that entire function. Now this one is precious. This one is telling us if I have a power, x to the n, I can always find the derivative of that function by taking this rule. It's our power rule. It's n, which is the power, and then times that function x raised to the n minus 1. Let's take a look. So if we had f of x equals x to the 6, the derivative function for that would be, I bring down the exponent, 6, and then I multiply it by this power, now 1 less than that, to the 6 minus 1, which would be 6x to the 5th. We see the derivative in action. So let's look at this problem. We have a child that inflates a balloon, admires it for a little bit, and then lets the air out at a constant rate. So V of t represents, V of t is the volume of that balloon. V of t represents the volume. And we're given that V prime, which is sketched below, is the derivative of that volume. So let's remember that in this problem, these are my y values. These are my y values. At t, the rate at which our volume is changing at time t is what is plotted. So let's answer these questions. And pause and see if you can get these knocked out. So for the first one, when does this child start to inflate the balloon? So now I'm looking at when the rate of that balloon increases. And I'm hoping that you can see that would be when t is 3. Now, when does the child finish inflating the balloon? So now let's take a look. So here, no rate. That balloon has not been inflated. Here, the balloon is being inflated and they are blowing air into that balloon at a faster rate as 3 progresses. Tell me what's happening in this interval. Well, what's happening is that kid is still blowing air into the balloon, but now it's at a constant rate. All right, people, what's happening here? That kid is still blowing air into the balloon, but they are losing breath, so they are blowing air in at a slower rate. So what is my answer for part B? They stop inflating that balloon at the second. So B, they finish inflating it at t equals 9. And I'm hoping maybe you look here and you can see this is when the admiration starts. They're just looking at the balloon. And now let's look at C. When do they start to let the air out? Boom, right here, because this is where the volume starts decreasing. So let's make something up here that's like T is 13.